So what we're going to do here is take a look at solving equations with simply one variable. Okay, the basic primary focus of algebra, right here. Solving a one variable, one equation system. Now you've learned about this, you've seen this before, but we're going to talk about some things throughout the process that might be different. So let's see where those are. We're going to call something a root. A root, if it's a value of a variable that makes the equation true. What's another word for root that you've used in the past? The blank of the equation.
Base. Base.
Base, not base. I could see that, base, root, being fundamentals. Makes sense. If I said to you, solve for x, you're finding the what? What's the term? The variable value, so you're finding the what? What are the directions you usually say when you're solving for a variable? It says find the value of the variable that makes it true, or the solution to the equation, right? So root is a mathematical term that just simply means the answer for the variable when solved in that equation. Take a look at the first one here. So solve the equation. So pretty much find the root. Okay, find the root. And we know there's only one root here because x has a power of 1. And we'll talk about that throughout the year, how the power of x indicates how many roots there will be. So to solve this one, how do I solve this one? Who can step me through this process? What's the easy way to solve this? Alex? Yeah, start by distributing, please. God bless you. By dividing by 3 or -7, you won't gain any ground. So I would definitely distribute first. Alex, what does that give me in the next line if I distribute?
That will give you 6x plus 15 equals -7x minus 63.
Now, at this point in time, you recognize that you have x on two sides of the equation. You have some constant that's on two sides of the equation. So we need to do what? What do we need to do at this point?
Move one variable to the next.
Yeah, pick which one though. Which one, Alex?
-7x.
Yeah, I would agree with you. I would always start by moving the negative one over because you can add it to both sides. Now, I could stop and write my next line of the equation down at this point, but do them both in one step, please. Okay, this is a bit of an accelerated class for that reason. Do them both in one step. So how do I get rid of the 15? I want variables on one side, numbers on the other. So get rid of the 15. Yeah, subtract 15 at the same time. And if you need to do what I'm doing here and use color coding, do that, please. So you recognize that you're doing it on the same side. So we add 7x to 6x, giving us 13x. And we have -63 minus 15, giving us -78. Now, again, please recognize that these 15s are canceling and these 7x's are canceling. That's why those just drop off. And we have two negatives, making it more negative. Solve for x. How do I solve for x, Danarsky? Yeah, divide. What did you get? Good. Okay, so if we recall this from middle school, we should remember that to get rid of something, we perform the opposite operation. Right? Currently, x is being multiplied by 13, so we divided by 13 earlier. Over here, 15 was being added to 6x, so we subtracted 15. 7x was a negative, so we added 7x to both sides. Okay, we always do the opposite operation as to what you see on in the equation itself. How do I know that this is right? Well,
You could check it by plugging -6 in for x.
yeah, you could check it in the original equation always, in the original always. Why? Let's see who knows their math. Why don't you check it in the middle? Like, why won't I take -6 and perform the check in this step? Or even in this step, I wouldn't really perform the check. I have to perform it here. Why can't I perform the check in this step or this step? Danielle?
Because if you check it in the middle, you might need an error before then, and then you're not checking your answer.
Exactly. You could check it in this stage, and it comes out right. You're like, oh, I checked it, it's right. But if you made an error earlier, you're checking it in an incorrect equation. So by default, even though you get a check and you're like, oh, this worked, it's not working actually there. Okay? So you need to check it in the original. Because let's say hypothetically that I thought, you know what, I thought negative 63 minus 15, I added 15 accidentally, right? And let's say I was like, oh, what a brain fart, but I had negative 48 here. And I did negative 48 over 13 and got another answer, and I checked that. And let's say I checked that right here. Well, it'll check out to be true. But if I check that answer that's incorrect back up here, it'll show you that the answer was indeed incorrect. Okay, so always check in the original. Second one on your own, go ahead. When you hit a point where you might be confused, feel free to look up. If you know what you're doing from this point on, keep going though. Because this might be a little confusing from this step on. Yes?
You want us to check every equation that we solve in your
One variable, one equation? No, definitely not. You should be able to do it. But when you get to the equations where there's possibly multiple answers, or there's square roots involved, or a system of equations, you should check it. But something like this you should be able to do. So what's the problem? Right, this problem here. What's the problem with this problem? Or with this example? Well, what's the problem?
It would come out to 0 equals 0.
Yeah, that's the problem we're getting. And not necessarily 0 equals 0. Be careful. I didn't get 0 equals 0, but you're right that you have no variable suddenly, right? The 3h is on both sides, isn't it? So to get rid of 3h, you would subtract 3h. Well, when you do that, you end up getting negative 8 equals 8. You get negative 8 equals... If you got 0 equals 0, it's different, that's why. You get negative 8 equals 8. Is that true? Does negative 8 equal 8? No, it does not. So what kind of an answer is this then? Anybody remember from their algebra class? What would you put as your answer for this?
No solution.
No solution. Okay, no solution. There's many ways to write this. I'm going to write it several ways. You could write null set. You could simply put an empty set there, like that. You could put a 0 with a line through it like that. These are all the same way to write the same answer. Okay, no solution, null set, empty set. Literally, the empty set with a 0 through it. Any way you write that is fine. In math, we call this a contradiction, right? Negative 8 does not equal 8. It's being contradictory. So there is no solution to this equation. There's no solution because their variable term dropped off. There was no variable in the end. If there's no variable, there is no solution here. Okay, but we're going to see in a minute where a variable could drop off and there still could be a solution. Let's see that one. Okay. Yes, sir?
Would you be able to graph that?
Would you be able to graph that? Meaning what? Graph each side of the...
If you graph this equation, would something pop up, or because it's no solution, would something?
Well, remember when you graph something, you're graphing a function or an expression. You can't graph an equation. If you move everything over to one side, you could graph what's left, or you could graph both sides of the equations and find the intersection to find the solution. And if you graphed both of these sides of the equation, you'd get parallel lines. They would never intersect, and therefore no solution. Okay? And we'll talk about graphing systems and how that works, the idea. But remember, you can't really graph an equation. You can graph one side of the equation, and you can graph the other side of the equation and find the intersection. And that allows you to find the solution. Okay? So for this one, we're going to do the same thing, right? We're going to distribute again. Oops, why did I put 18 there? Now, I got to this point, which you're probably all going to get to in a second or two, and at this point I could stop. I don't have to go any further. Why don't I have to go any further? What's happening here, Chandler? Yeah, pick any value of m. Literally, pick any value of m. Because both sides of the equations are literally identical, any value of m will work. 2 works, 3 works, 4 works, negative 274,333 works. Without even checking it, I know it works because I'm going to get the same value if I have the same expression on both sides. So any number works. So what do we make as a statement? M is infinitely many solutions. Good, that's one way to put it. What else? Anybody know what there's a term in math to use? Yeah, all real numbers. Okay? So you could start by saying M, this is a little bit of a weird notation, is in the set of all real numbers. M is a little like a squiggly E, means in the set of, it's epsilon really, all real numbers. Real numbers is a /R with a capital. Or you could honestly just put all real numbers. I don't care which way you write it. Okay? We're going to learn about interval notation later in the year, and I'll explain how that would look. But for now, I'm going to leave you with those 2 ways to write it. But this is different from the last problem. And the reason is this. If you tried to solve this, you would get 0 equals 0, wouldn't you? And isn't that true? Doesn't 0 equal 0? Yeah. When the variables all drop off and you get a true statement, it's all real numbers. When the variables all drop off and you get a contradictory statement, it's no solution. See the difference with that one? Yeah. Okay? So, all real numbers for this one, because any number will work. Now, graphically, Sarah, remember you asked about graphing the last one? These graphs are identical, aren't they? If you graphed 6m minus 9, it would be a slope of 6 with a y-intercept of negative 9. And the other graph would be the same. They would lie on top of each other. Therefore, every single point is a solution, because those are infinite intersections. Okay? And we're going to see that with systems also. All right. Number four, the formula that relates the height h in feet of a launched rocket t seconds after firing with an initial velocity v0 in feet per second is the following formula. H equals negative 16t squared plus v0t. Determine the initial velocity of the rocket if the rocket reaches a height of 40 feet after 2.5 seconds have passed. So we're taking a simple equation and simple solutions and applying this to a word problem now. Okay, we're applying it to a word problem. So I'm going to start by listing what I know. What is given to me is that we reach a height of 40 feet. So h is 40. After a time period of 2.5 seconds. So t is 2.5 seconds. And I'm trying to figure out what is the initial velocity. I have a physics problem for you, but we're going to see, well, you're going to see when you're juniors, that physics is math. It's applying math, though. So we take these 2 concepts here, these 2 known values, we can plug them in and solve for v0. That's what my equation looks like to start. I'm going to square my 2.5. I'm going to multiply by negative 16. All right, square the 2.5, multiply by negative 16. What do you get when you multiply those? 2.5 squared times negative 16. Jeffrey? Negative 9.98. Be careful. Oh, as a final answer? Sorry. No. Square, well, think about it. 16 times 2 is more than 9, so it can't be that.
Oh, no, I was squaring it 2.5.
Oh, okay, and then multiply by negative 16. What do you get when you multiply by negative 16? Be careful. You made a mistake somewhere. Check your work. Sarah? Negative 100. 2.5 squared, then multiply it by negative 16. Check your work again, okay? Feel free to use a calculator to square 2.5. I don't expect you to have that memorized. I really don't. Okay, so if you want to do 2.5 squared in the calculator and then multiply by negative 16, you can. Continuing to solve. How do I get rid of the 100 or the negative 100? Inigo, what do I do next to get rid of that negative 100? And then?
You just divide by 2.5 and you get yield equals
56. Very good. My units are feet per second. And that was given in the problem in the beginning. It was given in the actual problem. Now, I'm going to pose a question. Here's the question for you. What if I was doing the exact same problem again? And I said, you know what? That was the rocket that I launched, but Alex is launching another rocket, and his made it up to 70 feet instead of 40 feet. Right? So Alex did the exact same thing, and his, again, took 2.5 seconds, but it went all the way up to 70 feet instead of 40 feet. What would I do? I want to do this all over again, but it only went up to 70 instead of 40.
You just plug in a different H value?
Yeah, plug in a different H value of 70. Instead of 140, this would become 170. So you'd have 170 divided by 2.5 instead. Does everybody see how that would change? You're changing what's called a parameter. Something that changes, you learn as variables, but something that's made to change is called a parameter. So if everybody in the class did this project, and everybody at a different time and a different height, it'd be really annoying to resolve this like 10 times, right? So it's very useful to solve an equation for all variables. So we're going to go to the next problem now and see how that works. So we're going to solve for something in terms of the other variables. So instead of plugging in 40 and 2.5, we could have solved for V0 in terms of H and T and all these values. So let's do that in the next example. Take a look here. And that's what I wrote in the note, okay, at the top right there. When you're solving an equation in terms of other variables, consider those other variables to be constants. The last one was 56 feet per second. So in example 5, we're told that the volume of a right circular cone, right, a cone like an ice cream cone, with a height of h and a radius of r, is given by the formula v equals 1/3 pi r squared h. Solve this formula for the following. Solve this for the following. So in part A, I want to solve the formula for h. How would I solve this for h? And recall, okay, or remember, that you want to get rid of everything else that's around h, considering that maybe they're like numbers. Think of them as numbers. So Sarah, how would you begin this problem? I would start by multiplying both sides by the reciprocal of 1/3, which is indeed 3. That cancels this 1/3 with this 3 over here, giving me 3v equals pi r squared h. Absolutely right. What would you do next? Remember, we're solving for h. We're solving for h. If we're solving for h, think of v and r as numbers. If they were numbers, if r was a number, how would you get rid of it? If you had pi times 5 squared, how would you get rid of that 25 and that pi then? What would you do, Jeffrey? Divide. By? So divide both sides by pi r squared. On the right-hand side, those drop off, leaving you with h equals 3v over the quantity pi r squared. We're going to call this, and you want to jot this term down, this is a generic solution. Okay, a generic solution for h. So you've kind of solved for the height. Now, this enables me to have a very powerful expression, because I could tell you, Danielle, the volume is 5 and the radius is 2. But now I want you to do the same problem with a volume of 10 and a radius of 7. But then do it again for a volume of 30 and a radius of 3. And you could just simply plug in those numbers now, right? And it's so easy to calculate the height every time. Instead of plugging those numbers in the original formula and resolving this 4, 5, 6, 7 times. So what you've done is you've created like a little algorithm or a formula for h. And this is the beginning of something like computer coding. If you're going to do anything with computers, and you want to do anything with coding at all, you need to understand how to solve for a generic solution where the parameters volume and radius can vary. They can change. So maybe you're trying to find out the height, and you want the height to be 7. So you're trying a bunch of different values and radii. So you need to do it several times. So this is very useful to have an expression that represents the height, in which you can just try V and try an R. Or maybe you know that the radius can't be more than 7, because this cone has to fit in the box, and the box is 7 or 14 by 14. Right? So the radius can only be 7. You know that. So this has to be 7. So now you can figure out what your volume is and maybe get a specific height. Or you know what your volume is and see what the height turns out to be. But the idea behind a generic solution is that you can try many values of those parameters. How about part B? Part B. Solve for R. Same formula. And our goal now is to solve for R. Some of it's going to be the same, some of it will be different. What would I do first? What would I do first? James? Yeah, same as before, multiply by 3. Giving me 3v equals pi r squared h. Now, this is where it becomes different. Earlier, Jeffrey showed us to divide by pi r squared, so we were able to get this h by itself. But what are we trying to get by itself now? Chandler? R. So tell me real quick, what would I divide by?
H.
And what else?
Pi.
Good. Divide by pi h, giving you 3v over pi h equals r squared. And then take the square root to get rid of r squared. Tonight, section 1-7 homework. Okay, that was the last slide there. If you need to go through this one a little bit slower, I have a recorded video of this lesson already under Mr. Howell's videos on Moodle. You could look at section 1-7 and look at this last example a little bit slower again if that last part was a little bit quick. Under the homework, section 1-7. Your homework assignment is always in your notes. I'm not going to keep putting this in the homework. So tonight you're going to see the homework due tomorrow will just say 1-7. Okay? So look at your notes to see what the homework assignment itself is.